Hi everyone, this is going to be the start of the second part of section 4.3 where we began learning about the unit circle and reference triangles. So you might want to start off your notes by just doing a 4.3 continued. And if you remember from the first part of this, like I was saying, we talked about the idea of the unit circle and using reference triangles and reference angles in order to evaluate trigonometric functions that have angles that fall outside of 90 degrees. So we're going to do a little bit more practice with this idea, and I have 3 examples up here where we're going to use the idea of a reference triangle. The directions say find the following without the use of a calculator. So none of this is going to be inputted on your calculator. When you give me answers, you're going to give me answers in radical and fraction form. So the best way to look at this is to actually visualize the angle and come up with a reference angle. So the first one is the sine of negative 210 degrees. So with all these, you're going to draw yourself a little picture and you're going to draw yourself the angle. So negative 210 degrees, here's my initial side of the angle, and that's going to bring me 30 degrees past the 180 mark. So this is negative 210. That's my theta value. Now within that angle, remember when we go to create a reference triangle, we're going to pick a point on that terminal side and we're going to drop the altitude to the horizontal axis. So we create this triangle over here, right in here. That's a reference triangle. I'm going to blow that triangle up a little bit over here so that you can get a little bit better of a picture of it. So if that's my triangle, you need to determine how big that reference angle is. How big is this angle in here? So if the angle's 210, we went to the 180 mark, and I think I kind of said in the process of doing that this would be a 30-degree angle. This is the reference angle. Reference angle. And that's the angle that we're going to base all of our answers off of for an angle of 210 degrees. So we know that if we labeled this with a hypotenuse of 1, we're creating the scenario of a unit circle situation here. So our triangle has a hypotenuse of 1. The side opposite the 30-degree angle is going to be equal to 1/2, and the side opposite the 60-degree angle would be negative radical 3 over 2. Negative because it's along the negative x-axis, radical 3 over 2 because it's opposite the 60-degree angle. I'm only concerned with the sine of this angle, and remember, sine deals with the y-axis value if we're working with that unit circle idea. So my final answer, and your final answer, is going to be 1/2. The sine of negative 210 degrees is equal to 1/2. So everything, I can't stress the importance enough of those 2 special right triangles and understanding the ratios if you have a hypotenuse of 1. We'll try another one. This one's going to be in radian measure, so the tangent of 5 pi over 3. Let's try to work in radians rather than convert to degrees, even though I know some of you are going to do that. 5 pi over 3 is a positive angle measure. 3 pi over 3 would be a half of a revolution. So I need to go 2/3 more of another half of a revolution. That would bring me to 5 pi over 3. So we're probably, if this is the initial side, we're probably looking at this as the theta value. Somewhere in there. We know it's a 4th quadrant angle. So we need to create the reference angle, pick a point on that terminal side, create the reference triangle. And this triangle, since there's a right angle there, has a reference angle. This little angle in here is our reference angle. That's equal to how much? If our entire angle is 5 pi over 3, 1 full revolution would be 6 pi over 3. So this is pi over 3 short of that full revolution, which is what the reference angle will be. Pi over 3 is equal to 60 degrees. There's where you can make a equivalent connection to the degree measure. So the y-axis value will be negative radical 3 over 2. The x-axis value will be 1/2, since opposite the 60 is the bigger of the 2 sides. And if we want to do tangent, remember, of 5 pi over 3, That's going to be the y-axis value over the x-axis value as long as we're working with that hypotenuse of 1, although that's the case in all scenarios. So that'll be negative radical 3 over 2 over 1/2. If we flip this, and you should start becoming familiar with all of these ratios as well. Negative radical 3 over 2 is going to get multiplied by 2 over 1, and that leaves us with negative radical 3. So the tangent of 5 pi over 3 is formed from a right triangle, a 30-60 right triangle. 60 degrees is your reference angle, or pi over 3 radians. And then working with the ratio of y over x, or sine over cosine, we end up with the tangent of 5 pi over 3 equaling negative radical 3. One last one. We're going to work with secant this time. And if we draw ourselves a picture here, the secant of negative 3 pi over 4. So a negative angle again, just like in the first problem. If our initial side is here, negative 4 pi over 4 would be a half of a revolution. So negative 3 pi over 4 is going to be 3/4 of a half of a revolution, which means the theta value is right here, negative 3 pi over 4. The reference triangle that's created, we'll pick a point on that terminal side, we'll raise the altitude up, and that reference triangle that's created this time is a 45-45 triangle. So this reference angle in here is pi over 4 radians, or 45 degrees if you're thinking in terms of degree measure. That makes each of our legs radical 2 over 2. They happen to both be negative this time though, because this angle is falling in the third quadrant. And if we're looking for the secant of this angle, secant of negative 3 pi over 4, secant we know is the reciprocal. So the secant of negative 3 pi over 4 is the reciprocal of cosine. So it's 1 over the cosine of negative 3 pi over 4. And the cosine is the x-axis value, so we're going to flip the cosine value, which is equal to 2 over negative radical 2, which if we rationalize becomes 2 radical 2, this is all going to be negative, over 2, which is just negative radical 2. So secant of negative 3 pi over 4 is equal to negative radical 2. Not too tough. The key, again, remember, is knowing these two triangles, that 30-60, 90, and the 45-45, 90 ratios. If you know those, you're good to go. And you just have to know how to set up that reference triangle, making sure that the altitude is drawn according to the horizontal axis. So write down any questions you might have on those problems. Bring those questions into class with you so that we can talk about them. And we'll do some more practice problems with that so that you can do some things on your own and I can see how you do with that. Okay, here's a different type of a problem, not laid out so specifically. This example says find cosine and tangent. So cosine and tangent, we're only finding 2 of the 6 trig functions by using the given information to construct a reference triangle. So what we know in the first problem is that the sine of theta is equal to 3/7, and we also know that the tangent of theta is less than 0. So that little additional piece here, we're not given an angle measure this time. It's just a generic angle theta, which means we have to figure out where this angle falls. We have 4 quadrants to choose from, so we kind of have to make a determination. And we know that according to ordered pairs, if we can figure out the positive, negative signs of the coordinates, we can figure out the quadrant the angle falls in, and then we can make a properly labeled reference triangle. So if my sine value is positive, that's my y-axis value, and tangent is negative. Since we know that tangent is sine over cosine, that forces my x-coordinate to be negative, which means that this is really going to be a quadrant 2 angle. So when I draw my scenario for this, I'm going to draw it in the second quadrant. Think about that. Sine is positive, that's the y-axis value. So that's the y-coordinate. Tangent is negative. If tangent is negative, which is sine over cosine, then that means that your cosine's got to be negative, which is forcing this into the second quadrant. So we'll draw a second quadrant scenario. So we're just putting this angle this time instead of trying to be specific like we were last time. Here's my initial side, second quadrant angle. Doesn't matter where it goes, but I am going to pick a point P on that terminal side. We'll draw a reference triangle, and this angle in here is my reference angle. That's alpha. So I don't know how big alpha is this time, but what I do know about the situation is that the sine of the angle theta, this is theta, the sine of the angle theta is equal to 3/7. Since we can use a reference triangle in order to help figure out that ratio, I know that the opposite over the hypotenuse looks like this. So the vertical leg is 3 and the hypotenuse is equal to 7. If we can figure out the horizontal leg, this leg right here, then we have our triangle completed and we can figure out the cosine and tangent by using SOHCAHTOA or using the idea of x over r, that kind of thing. So we know since this is a right triangle that we can find that missing side by doing 7 squared hypotenuse squared minus leg squared will give us the other leg. So 49 minus 9, x squared will be equal to 40, and x will be equal to the square root of 40, which is, what are we doing, 2 radical 10. If I computed that correctly. And because it's along the negative x-axis, we're going to say negative 2 radical 10. So that means that the cosine of this angle theta, I think at this point it's almost easiest to go back to the SOHCAHTOA idea. Cosine, remember, is adjacent over hypotenuse. So negative 2 radical 10 over 7. And the tangent of theta is opposite over adjacent. So negative 3 over 2 radical 10, which we will rationalize to negative 3 radical 10 over 20. So those are our two values. So all based again off of a reference triangle. The difference in these problems is that you don't know where the angle falls initially. You're given a generic angle measure. We need to determine what quadrant the angle falls in, and then make your reference triangle, figure out the missing side, and then compute through SOHCAHTOA. I think that's the most straightforward way, those trig ratios. So I'm going to erase this picture and this work so that I can fit the work for the next problem there. Make sure that you write down any questions from this one. You might need to rewind if you want to just revisit it again before we go on to the second one. So this one, secant is equal to 3 and sine is greater than 0. So according to the ordered pair scenario, if sine is greater than 0, I know that the y-coordinate is positive. Secant is related to which trig function? You're right if you were thinking cosine. So if secant is positive, then cosine is positive, which means we're dealing with a quadrant 1 angle. So we'll draw the reference angle. Although this time we don't need a reference angle because it's in quadrant 1. So here's my angle. So this is theta. Theta also happens to be the angle I'm going to measure off of because it's within the first quadrant. And we know that secant is equal to 3. Now, right off the bat, since we're being asked to find cosine and tangent, remember that's the object of this problem here. We're being asked to find cosine and tangent. I can answer the part about cosine because cosine and secant are related by reciprocal properties. So the cosine is equal to 1/3, which means that the adjacent and the hypotenuse can be labeled as such. The adjacent side is 1, the hypotenuse is 3. I need to find tangent, so I need that vertical leg. So we can say 3 squared minus 1 squared is y squared. And that means y squared will be equal to 8 and y will be equal to 2 radical 2. So this leg is 2 radical 2. And that's going to make the tangent of theta, which we can go back to SOHCAHTOA in the picture, is opposite over adjacent, 2 radical 2 over 1, or just 2 radical 2. So the cosine of theta is equal to 1/3. The tangent of theta is equal to 2 radical 2. Again, forming that reference triangle worked out pretty nicely in this problem because we were in the first quadrant, so there wasn't too much to do. One more, just to make sure that you get the idea. In this one, the cotangent is undefined. Cotangent is undefined. Secant is negative. So we've got to come up with a scenario for the ordered pair. If cotangent is undefined, that means that tangent is equal to 0 because they're reciprocals. So I can already answer part of this problem. If tangent is equal to 0, I'm thinking back to when I worked with the unit circle, and I'm not quite sure if I can come up with a triangle for this because the tangent seemed to appear to be 0 when we were falling on a quadrant, on an axis line. So I can't really, if secant is negative, that means cosine is negative. But because this is undefined here, this is an axis line then that this angle is falling on. In fact, it's falling on the negative x-axis line because of the fact that the x-axis is negative there, or the x coordinate is negative there. So my picture looks like this time. There's actually no triangle here. The angle measure, if this is the initial side, then the terminal side is falling on that negative x-axis. So this is my theta value. So if I force the scenario to be negative 1, 0, kind of like using the unit circle idea, then that means that the cosine of theta, I already did tangent from the original, the cosine of theta will be equal to negative 1. That one might be a little hard to understand and wrap your mind around. So think about it for a few minutes, rewind, definitely put a little star by it, and we can talk about it a little bit more in class with how to determine if this actually falls on an axis line like this one did. Okay, not too much more. Almost done here. We're going to do a little section on these quadrantal angles, even though we talked about them together a little bit in class when you were filling in your unit circle. But to get some formal notes in your notebook, a quadrantal angle, kind of a weird word, is an angle whose terminal side is along one of the axis lines. So the terminal side is along one of the axis lines. So pi over 2, which is 90 degrees, 270 degrees, 6 pi, all of these angles have their terminal sides on an axis line. So we're going to do a couple problems where we're going to evaluate quadrantal angles. The cosine of pi over 2. Cosine of pi over 2 means that we're starting with our initial side and, whoops, here's our terminal side. So this is the point 0, 1. Remember, cosine deals with the x-axis value, so the cosine of pi over 2 is equal to 0. Shouldn't be too hard as long as you can figure out where the angle falls. The sine of negative 270 degrees. Negative 270 degrees. If we go, here's our initial side. Negative 270 is going to bring us in a clockwise direction, which will have the terminal side ending right here. Looks very similar to the angle that we just drew. I suppose I should have put the angle mark in the first problem over there. This one is going to be indicated in this direction. And we still have the same ordered pair, 0, 1. But the sine value this time, remember, is the y-axis value, so that's going to be equal to 1. The tangent of 3 pi over, just 3 pi, tangent of 3 pi, which is example C. We'll draw where that angle falls. Now, tangent of 3 pi, if we go around one full revolution, here's my initial side, one full revolution is 2 pi. So we need to go another pi, which is going to be another half of a revolution. So the terminal side will be over here, but if we draw the angle, it looks like this. So that's 3 pi. The point that would fall on that terminal side would be -1, 0. And tangent, remember, is y over x or sine over cosine. So the tangent will be 0 over -1 or 0. So we have two answers of 0 in this section already. And the last one, the secant of 11 pi over 2. So where does 11 pi over 2 fall? Let's see, 11 pi over 2. 4 pi over 2 is 1 full revolution. So here's the initial side. If we go around, this is 4 pi over 2. This is 8 pi over 2. 9 pi over 2. 10 pi over 2. 11 pi over 2. So our angle is stopping right here. Pick a point. This point is the point 0, -1, if we're doing this according to the unit circle idea. The secant is the reciprocal of cosine. So the cosine is equal to 0. If we flip 0, we've learned that we get undefined. So the secant of 11 pi over 2 is undefined. Not too tough. It's just, you've got to think about every quadrant is another 90 degrees. So if you can figure out where those angles fall, you're strictly using the 0 and 1 idea. You're not drawing any kind of a reference triangle when you have an angle that's considered to be a quadrantal angle. But again, as I always tell you, write down questions that you might have and we can discuss these together in class. Last topic within this section. Every single trigonometric function, we're going to start this out by talking about every single trigonometric function. If you look at your trig chart, the trig value chart that you filled in, we talked about the fact that there are patterns. And these patterns relate to what's called the period of these functions. So every single trig function, trigonometric function, a trig function is periodic if there is repetition in the trigonometric values as it moves around the unit circle. So when you look at your trig value chart, I want you to kind of check out where you see the repetition. Over how many degrees or radian units do you see the repetition occur? So the period, here's the definition of the period of a trigonometric function, refers to the smallest number of degrees or radians in which that repetition occurs. So if you pull your trig chart out, I want to stop this for a second. Pull your trig chart out just to check it out for a second and look at it and see what you can make of that trig chart and see where the repetition actually occurs. If you look really, really, really closely, you're going to notice that there really isn't repetition for sine, cosine, cosecant, and secant within that chart. There's a pattern, but there's no actual repetition. But if we were to go past the 360 degrees or 2 pi radians, that entire chart would start over again. So the period of sine, cosine, cosecant, and secant is 360 degrees or 2 pi radians. So that means that the values of the trig functions repeat every 360 degrees or 2 pi radians. It's a little bit different for tangent and cotangent. So take a peek at the tangent and cotangent columns in that chart. And I want you to see what the smallest increment of degrees or radians is before you start to see exact repetition again. So if you look at that, you should be seeing that every 180 degrees or pi radians is when tangent and cotangent repeat. So the period of sine, cosine, cosecant, and secant is 360 degrees or 2 pi radians. And tangent and cotangent is 180 degrees or pi radians. That's important to know. You should memorize that, those two ideas, because we'll use it if I ask you to do something through the idea of the functions being periodic. We're going to run through, that didn't work. We're going to run through a couple problems on the next screen that are going to illustrate the use of the functions being periodic. And then we're going to be completely done with this section. So this example says find each of the following without a calculator. I think I'm going to add to the directions use the concept of trig functions being periodic to answer this. Because we could get away by doing this through reference triangles and quadrantal angles as well. But we're going to try to incorporate the idea of functions being periodic, which is going to give you just another tool in order to work with all these trigonometric functions and ratios. So the sine of 17 pi over 4, what we know about the sine function is it repeats every 2 pi radians. So that means that if I took away, because we know that 17 pi over 4, I hope you realize that this is greater than 2 pi. This value, this angle measure is greater than 2 pi. If we took away multiples of 2 pi until we knocked it down to the smallest possible positive angle, then we could actually compute the trigonometric ratio without, doing a reference triangle and that kind of thing. So the sine of 17 pi over 4 is exactly the same as the sine of, if I do 17 pi over 4, how many groups of 2 pi can I take away? Well, 2 pi is the same as 8 pi over 4. So I can take away 2 groups of 8 pi over 4 from this original angle measure to reduce the original angle measure down to the sine of just pi over 4. Because 2 times 8 pi over 4 is 16 pi over 4. So the sine of 17 pi over 4 minus 16 pi over 4 leaves us with just the sine of pi over 4. What this is saying is that the sine of 17 pi over 4 is exactly the same as the sine of pi over 4. It's as if we're saying if we graph 17 pi over 4 on the coordinate plane, pi over 4 would be your reference angle that you're working with. So this is another way to kind of identify your reference angle without drawing the picture out. And we should all know that the sine of pi over 4 now is radical 2 over 2. If you did not know that, then you'd have to go through and probably draw yourself a picture. But I'm hoping by this point in time, this is coming pretty quickly to you because that's what the expectation is. So that's an example of using the idea of the function being periodic in order to reduce it down to a value that we know right off the top of our head and then evaluate. The cosine of negative 5 pi. So the cosine of negative 5 pi could be rewritten. Now cosine again has a period of 2 pi. So this time I think what I'm going to do, because I know the values in terms of the positive angle measure, is I'm going to take the negative 5 pi and I'm going to add how many groups of 2 pi? I think I'm going to add 3 groups of 2 pi onto this, because what that will do is it will bring me into the positive realm of things. This will give us the same as the cosine of pi. Now the cosine of pi is the 180-degree angle, and the x-axis value there, because cosine deals with x-axis, is negative 1. So the cosine of negative 5 pi, through the process of using the fact that the functions are periodic, is equal to the cosine of pi, which is equal to negative 1. Now I suppose someone in here could have just added 2 groups of 2 pi, 2 groups of 2 pi, which would have brought you to negative pi. And negative pi is pretty easy to visualize to and get the answer to. So there's more than one way to look at this. But we're using the idea, this work right, whoops, moving things suddenly. This work right here, right in there, is using the example of the function being periodic. So the cotangent of 5 pi over 4 is our last example. 5 pi over 4, cotangent repeats every pi radians. We're doing all these in radians because I want you to kind of be forced to think in radian measure. So I could conceivably say that I could take the cotangent of 5 pi over 4 and subtract 1 group of pi, which is the equivalent of 4 pi over 4. So the cotangent of 5 pi over 4 is exactly the same as the cotangent of pi over 4, which in turn tells us when we have a pi over 4 radian measure or 45 degrees, tangent and cotangent are both equal to 1. So the cotangent of pi over 4 is equal to 1. And that, again, it's going to come with learning those values. You need to really put some time into understanding at least the first part of that chart, the first quadrant of that chart, because we can always reduce things down into that scenario. So that's it for this video and really the end of 4.3. Topics covered here. We did a little bit more work with the reference triangles. We did a little bit of work with the idea of a generic angle. We talked about quadrantal angles, and we talked about the trigonometric functions having this property of being periodic. So those are the final 4 concepts in this section. Again, make sure that you review what you need to look at again, and come into class with any problems, any questions, and we'll work on a problem set when I see you next time. Thanks for listening, and I'll see you soon.